Okay, in this video we're going to talk about some of the rules of probability. So let's just go ahead and jump right in. In the last video we defined what an event was and what an experiment was, and so now we're going to talk about the complement of an event. So if we have some event A and we know that we can draw a Venn diagram that shows us the representation of that event A. This is what we get here. So the rectangle is universe, A is here. The complement is anything that's not in A. So here's A, and A complement is everything that's outside of that circle. So there are lots of different notations that are used for complements. This textbook is going to use A prime. And you'll notice that if we combine A with A prime, or A complement, we get the entire sample space. So that tells us that the probability of A plus A prime is equal to 1. Or, in other words, we can use some algebra and find out that the probability of A complement is 1 minus the probability of A, which I think makes good sense. But that is going to be one of the more useful things that we're going to have available to us as we go through this course. So it's going to show up all the time. It's very important. Okay, the next rule is what we call the union of two events. So if we have event A and event B, and we want to say that event A has taken place or event B has taken place, we say that's the union of those two events. And we use this notation here, A union B. And if we draw Venn diagrams, the easiest way to see this, we're saying everything that's in A or everything that's in B, or in the intersection of the two. What's the intersection? Well, that's what we're going to talk about now. The intersection is everything that is in A and in B. So think of it as and here. The notation is this upside down union. So you can think of that as kind of the opposite of the union. And so we say if it's in A and it's in B, then it's in this intersection right here. This also has another name. It's called the joint probability. So what's the joint probability of the event A and B? That's just the probability of the intersection, or the probability that both of those things are going to occur. This brings us to what we call the general law of addition, and that states that if we have two events, A and B, the probability of the union of those two events, A and B, is just equal to the sum of the probabilities of the events, A plus B, minus the probability of the intersection of those events. So why do we minus the probability of A and B? Well, it's because that's included 2 times when we add the probability of A plus the probability of B. The Venn diagram that shows us that. I love those effects. So there was A, there was B. So A and B got added in 2 times. You can see that it's purple and green in this video. So we have to subtract it 1 time in order to be able to get the correct probability for the union of A and B. So here's an example of the general law of addition using a standard deck of cards. We could say, what's the probability of a queen? Well, there's 4 queens in the deck, so this is the classical approach, or the a priori approach to probability. There's 4 queens in the deck, and there's 52 cards in the deck, so the probability of drawing a queen would be 4 out of 52. And we could say, what's the probability of drawing a red card? Similarly, we have 26 out of 52. And now the question becomes, what's the probability of a red queen? And it turns out that there are 2 out of 52 red queens. That makes sense to us. And so then finally we can find the probability of a queen or a red card, and that's just going to be the probability of the queen plus the probability of a red minus the probability of a queen and red, minus the probability of a red queen. So we plug those numbers in. and we see that the probability is 28 out of 52, or a little bit over 53%, or almost 54%. This leads us to talk about what's called mutually exclusive events, or disjoint events. So if A and B are both events that are mutually exclusive, then what that means is their intersection is the empty set or the null set, and that means it contains no element. So it's easy to see this in a Venn diagram. Here's A, here's the event A, here's the event B, and they don't overlap. So there's no intersection between the two. And if there's no intersection, then the probability of the intersection is 0. And so that gives us a special law of addition, which says if we have mutually exclusive events, then there's no intersection. So this part right here is always 0, so we can just forget about it and never have to write it out. So now we're going to talk about what are called collectively exhaustive events. And events are collectively exhaustive if their union is the entire sample space S. So A and A complement are always collectively exhaustive. And this is an example with just two events. In other words, there's never just one possible outcome from an experiment. If there is, it's a very boring experiment. I guess it can happen. But if there is just one outcome that you're interested in, heads, for example, when you're flipping a coin, that implies that there is at least a not heads, and generally we call that tails. Although it is possible to have an event that takes up the entire sample space, which means the complement would be the empty set. So there always are at least two, and there can be more than two. In other words, we could have a Venn diagram that contains more than two events that take up the whole thing, and that's what we would have here if we're talking about our shopping spree at Walmart, or method of payment at Walmart. We've got 4 different options: credit card, debit card, cash, or check, and those are the only ways to pay. So those take up the entire sample space. We would call those collectively exhaustive. Back here to the collectively exhaustive events of 2 possible outcomes, we call those dichotomous events or binary events, and that's when there's only 2 possible outcomes. For example, does your car have a warranty, A, or not have a warranty, A complement? Those are the only 2 possible possibilities when it comes to the status of your car's warranty. Either you have a warranty or you don't have a warranty. Okay, so let's move on then and talk about what's called conditional probability. Conditional probability says I have some event A, and I want to know the probability of that event A, but I have some information, and the information I have is that the event B has taken place. So given that B has taken place, I want to know what the probability of A is. And that oftentimes is different than the probability of A all by itself. The probability of A all by itself would be the unconditional probability. But we would write that as the probability of A. This is unconditional. Probability of A. But we're talking about the conditional probability, so we're going to denote that. We're going to say B has taken place. So this pipe here, this line, vertical line, says given. So the probability of A given B is what we're talking about. And we can write that as the probability of the intersection, probability of A intersect B divided by the probability of B, whenever we have to, this is a very important point, probability of B has to be positive, greater than 0. So here's the logic behind that. Given that B has taken place, I know that something has happened inside of this green circle right here. And that now becomes the sample space, if you want to think of it that way. It's the entire collection of possible outcomes. And now I want to say, what's the probability that A took place inside of that? And so the only way A can take place inside of that is if the intersection of A and B takes place. And so if I take the probability or the the probability of the intersection of A and B and divide that by the probability of B, that will give me the conditional probability of A given B. So let me say that again. The sample space is now restricted to B. B is like the universe. That's all that's ever going to happen. The intersection of A and B is the part of B that also has A in it. So if I want to know the probability of A, that's going to happen. It's going to have to happen when the intersection occurs. And so then the ratio of the relative size of A intersect B to B is that probability. So it turns out the law of complements still holds here as long as I condition on B. So let's look at an example that is kind of a fun one. If you go to the county fair with maybe you did this as a kid or with a bunch of your friends at some point, there's oftentimes booths that are set up where people try and take your money from you, but they give you opportunities to win prizes and so forth. So let's say you go to one booth and they say, okay, here's the deal. We've got 3 cards. One of them's red on both sides. One of them's red on one side and blue on the other side. And the other one's blue on both sides. And so the guy running the show says, give me $1, and if you can tell me, you know, if you win this prize, win this game, I'll give you a big stuffed animal or something like that. And so the guy says, okay, here's how it works. I'm going to have you randomly select one of these cards without being able to look at them. And then I'm going to show you one side of the card, and you'll know whether you're looking at red or blue. And then the question is, what's the other side going to be? So there's two possible outcomes, and so you have to come up with those possible outcomes. So what we're interested in then is what's the probability of seeing a red side, or rather the other side, side number 2. I'm going to write R2, given that the first side is red. So the guy pulls out a card, or you pull out a card, and you see a red side. And the question then is, what's the probability that the other side is also red? Now, if you were to do this kind of naively and say, well, let's look at the classical approach to probability, and that says that there's 2 possibilities for the other side. It's either blue or it's red, and so red is only one of those. So that probability should be 50%. Oftentimes people look at this problem and think that, but it turns out that's not quite true. In fact, what we have to do is use conditional probability to say, what's the probability of seeing a red side on the first and a red side on the second, and we divide that by the probability of seeing a red side the first time. And I wrote this without the intersection here, but that's sometimes that's done. If it's just R1, R2, that means the intersection. I'll put it back in now. So I think it's pretty easy to make the argument that the probability that the red side was shown, that we saw a red side on the first side that we saw, is 1/2, because there are 3 red sides, 1, 2, 3, and there's 6 total sides. So we're going to have 1/2 in the denominator. And now the question is, what's the probability that we saw the red side, the first side we saw was red, and the second side we saw was red? Well, the only way this can happen right here is if we pick this card. And so what's the probability that we pick that card? It's 1/3. So 1/3 divided by 1/2 turns out to be equal to 2/3. And so if you see a red card, if you see a red side of a card, the probability when you flip it over and look at the other side that it's also red is 2/3. Where most people get this confused with the half and say, well, there's a red and a blue still on the other side. So what's happening here is if I pick this card right here, there's actually two different ways that we can get a red side that we look at. And if we pick this card, there's only one way that we can get that red side. So of those three total ways that we can get the first card being red, two of those come from selecting this card, so two reds, and only one of those comes from this card. So that means turns out we're twice as likely to see two reds than we are to see just the red and the blue card, given that information. So this whole notion of conditional probability is very important because it talks about how we can change our assessment of the probability given that we have some information. And that's something that's very important because we have all sorts of situations where we're given information and we need to incorporate that into our assessment of probability. So this is such an important topic. We're going to look at another example of it and define what we call the general rule of multiplication, which says I can write the probability of the intersection of two events as just the product of the conditional probability of one event given the other event times the unconditional probability of the other event. So in other words, all we did was say, let's take this conditional probability and we're going to bring this over here and then write down this probability of the intersection. So here's an example. We've got a population of kids that are not in college, 16 to 21, and they're either unemployed, they're high school dropouts, or they're unemployed high school dropouts. All right, so it's possible to drop out of high school but still have a job, and it's possible to be unemployed and not have dropped out of high school. So what we're interested in then is the conditional probability that a member of this population is unemployed given that they dropped out of high school. All right? So we want to know, given that they dropped out, what's the probability that they're unemployed? And that's different than saying what's the probability that they're unemployed and dropouts. We already know that probability is 5.32%. So first we need to define U as the event that a person is unemployed, D is the event that a person dropped out of high school, and write down what these probabilities are. We have 13%, 13.5%, 29.05%, and 5.32% respectively. And so now we can say what's the probability that somebody's unemployed given they are a dropout. Well, given that you're a dropout, that's now the relevant universe. So the biggest that probability is going to be is 0.29. How much of that is made up by the unemployment category? Well, it turns out to be just the intersection of that with D. So we get about 18.31% for the probability that somebody is unemployed given that they're a dropout. And if you compare that with the probability of being unemployed, that's higher. And so this gives guidance counselors and high school teachers and parents the ammunition they might need to come back and say, look, if you drop out of high school, things aren't going to be as good for you as if you stay in high school. In other words, there's a higher probability of not getting a job if you drop out of high school than if you don't drop out of high school. And so we can see that here when we make that comparison. The last thing we're going to talk about in this video is the odds of an event and being able to calculate the odds of an event given from a probability. The odds of event are something that we often hear, and the odds in favor of an event are just the ratio of the probability of the event to the probability of the complement of the event. And when we use the term odds, we can almost use it in place of probability, keeping in mind that odds are now going to be the ratio of the probability instead of just the probability. So if I say the odds of some event taking place, and those odds are very high, I would then be able to determine that the probability of the event taking place is very high. Oftentimes in sporting events in particular, when they say the odds on some game, for example, or some horse, usually they're giving the odds that the horse is going to lose. So it's the odds against. And so you want to be careful with that. If you're talking about the odds in that context, make sure you know that it's odds in favor or odds against, and then make sure you're going to be able to calculate the probability correctly. Otherwise, you might say, well, if the odds are 5 to 1, what does that mean? That means the probability of winning is 1 out of 6. All right, so how would you figure that out? We would do as follows. If the so before we get there, the odds against an event occurring are the probability of it not happening divided by it happening. Again, this is the one that's typically given when they're talking about the odds of a horse winning a race, or some team winning a basketball game or football game or something like that. So if the odds against an event are quoted as B to A, then the implied probability of the event A is A over A plus B. So as I said, if the odds are 5 to 1 for someone winning or a horse winning a race, then the probability that they're going to win the race is actually 1 over 6, so 1 over 1 plus 5. So you got to be careful if you make sure you understand if it's odds in favor or odds against when you're talking about gambling and so forth. And here's that same example except for 4 to 1 instead of 5 to 1. The probability of winning for a horse, so the odds against a horse are 4 to 1, and so the probability of winning is 1 over 5. And again, this is something that's oftentimes used just with the subjective approach to probability, and if you think that the odds are different, I mean, how do you come up with 4 to 1 for odds against a horse winning? Well, there's guys who sit around and study horses and trainers and bloodlines and weather conditions and all of this information they've got available, and then they come out and say, well, I think this horse is going to win, this horse is going to take second, and so forth, and they come up with what they think the odds are, and they're willing to pay. They're confident enough that they're willing to pay or bet on this probability. And so people come along and say, I think something differently. I think this other horse is going to win or has a higher chance than that, so I'm going to take the chance to make some money. And again, that's an example of the subjective approach to probability. So we're actually not going to do too much in this class with the odds. I think there might be 1 or 2 homework questions, but we're going to deal mainly with probabilities. So that's the end of this video. We'll finish up Chapter 5 in the next 1 or 2 videos, maybe 3, depending on how quick we get through them. So we'll see you in the next one.